Today we're going to be looking at simple linear regression. It's a new technique. It's based on some of the work we've done previously. I'm going to be walking you through the PowerPoint slides and explaining what you're looking at. It's a little bit more complicated, but I think you'll do just fine. All right, simple linear regression. What are we talking about? Well, a simple linear regression is basically the same thing as a bivariate correlation. So we did some work with correlations previously. Bi meaning two, variate meaning variables. So the relationship between two variables, and we used scatter plots to investigate those relationships to get a visual representation of what we were looking at. So here's an example of a scatter plot showing the relationship between height and age. In this case, age is on the x-axis because age in years, so y standing for years, not y-axis. Age in years is on the x-axis because it's supposed to predict the dependent variable, the outcome variable, which is height. So as you get older, you get taller, and those who are younger are shorter. This is a positive correlation because as one variable goes up, the other variable goes up. So up here we have 12-year-olds. 12-year-old children right here, and there's still some variation, so not every 12-year-old is exactly the same height. There's some variation. And here's our 4 or 5-year-old, and again there's variation in the heights, but you can see that in general those kids are shorter than the kids here, and as you get older you get taller. So this is sort of how we'd visualize a correlation. So we're going to be doing something very similar here. Uses two variables, so predictor and outcome variable. And so you're using the predictor to predict the values on the outcome variable. So instead of just looking at the strength and direction of correlation, we're interested in a predictive relationship. We want to be able to say something about one variable with knowledge of the first. Okay. A regression line, so that's what you're looking at right here. This is called a regression line, is drawn through the scatter plot of the two variables, so all these points. And the idea is that this line minimizes the distance between all these points. So if you took that distance and this distance and this distance, you took all of them together of every single one of these points, then this line is the one that I guess fits the best between all of those. The equation of this line is what you use to make predictions about new observations in the future. So this is an inferential statistical technique. You look at a sample, so let's say this is simulated, but let's say this is a sample of a whole bunch of children in some community, some sort of homogeneous community, and now we have a new student, our new child, and we say, okay, we know this about other students. This child is 8. How tall do you think this child will be? And so basically use this to say, well, I predict the child will be this tall. Of course, we understand there's going to be some variation. We don't know exactly, but that's our guess, and it certainly gets us closer than having no idea. Okay. Well, why would you use this kind of a model? Well, let's look at the value of this. So let's say now we're not worried about children, we're thinking about cars. So we're interested in the horsepower of an automobile, and we want to know what will the horsepower of a particular car be. So this could be a situation where maybe you manufacture automobiles and you have some thought about what you want the horsepower to be, but you're not really sure how to predict that, how to know how it's going to turn out. So without any kind of a regression model, any kind of model, your prediction is going to be the mean of the variable. So let's say you have a sample of all the cars, or I guess it would be the population, all the cars, and so 149 cars, and we know the range for horsepower is 55 to 450, so really a car that's not very powerful to one that's really powerful, and the mean is 185. So the average horsepower of a car is 185. So no matter what car we're talking about, we'd always predict that the horsepower is 185. So if somebody said, hey, I have a Ferrari, what do you think the horsepower will be? We'd say 185. Hey, I have a golf cart, what will the horsepower be? 185. No matter what car you come up with, the prediction's always going to be 185. Well, that's not super helpful because, of course, there's going to be all kinds of variation in that. So So let's say we're talking about a Ford Focus. That's what my wife drives. So if we know, all we know is the mean horsepower, we predict that the horsepower of the Ford Focus is 185. What if it's a Chevy Corvette? Same thing, 185. So you can see without any additional information, our prediction is fairly limited. That's better than having no information. If we didn't know the mean, if you asked, a kindergartner, what do you think the horsepower is of a Ford Focus? They might say 2 or a million. They have no idea. So having the mean gives us something, but not enough. So now let's say we have some new information. We are told the engine size of each of these vehicles. So we know engine size in liters, and we know horsepower. Now we can create a scatter plot to look at the relationship or the correlation between these variables. Since we can see that there's a linear relationship, it forms a line, we can use a regression model to make better, more informed predictions. So again, we see that there's a positive linear relationship. As the engine size gets bigger, the horsepower goes up. As the engine size gets smaller, the horsepower goes down. So this car with a very small engine size, very little horsepower. Big engine, big horsepower. Okay, so again, without the regression model, all we have to go on is the mean. So I drew this red line here to represent the mean horsepower, which is 185. So here's the entire range. I guess about here to about here. So there's a little extra space up here. And then the average is 185, so that goes across here. So you can see that a lot of the cars are above, especially that one, are above the mean, and a lot of the cars are below the mean. So if we were to guess 185, there's going to be a big chance we're going to under or overestimate the mean, or the horsepower. Okay, so here's an example. So this car, it looks like it's about maybe 350 is the horsepower. If we guess that this car had a horsepower of 185 based on the mean, we're going to underestimate it by quite a bit. It's way more horsepower than that. In the same way, if we guess that this car had a horsepower of 185, we would be underestimating that value. So you'd say, oh, I bet he has 185. Oh, no, it's more like 50 or 55 right here. Now that we have the other information about the engine size, we can create this regression line. So again, this line is basically sort of it minimizes the distance between the points. So you could think of it as the slope of this relationship, which can be graphed in a mathematical equation. So now our predictions, knowing this, are going to be much more accurate because we're going to make the predictions using this regression line. So I'll show you what we mean by that. So here's the point that we were looking at before. Go back a couple slides here. So before, we guessed that the horsepower was 185 based on the mean. That's all the information we had. And now we can see how off we were. We're really far off. But now we're going to use our guess based on the regression line. So based on that, it looks like we're guessing about 300. Now the distance is very small. We've barely underestimated it at all. And before, we underestimated it by a whole lot. So old prediction, new prediction. Old prediction, new prediction, old prediction, new prediction. So the old prediction was based on the mean, the new prediction based on the regression line. So that's way better. It gives us more what we call predictive power. I'm sure we'll talk about this later, but you remember we used R in the past, and that's a measure of the strength and direction of the correlation. And then we talked about the coefficient of determination, which was R squared. And that told us the amount of variation in one variable that's explained by the other. Whenever we create that regression line, we're going to get an R squared value. So it's capital R squared. And here it's 0.72. So that means that one variable, engine size, explains 72% of the variation in horsepower. That's pretty good. It's very useful. Now the distance, there are very few points are going to be right on the line. So maybe that one, maybe that one, maybe that one. Maybe kind of that one. So there's 3 or 4 points. Out of all these cars, only 3 of them were right on that line, or even super, super close to it. So there's always going to be, or almost always going to be, some distance between the line and the actual value. So the line is what we call the predicted value. So I predict it will be here. The actual value is here. So there's a distance, and the distance between those two points is called the residual, or error. So we could say, if you had a point way up here, there'd be a large residual. If it's really close to the line, a very small residual, a very little error. And the distance we refer to as the residuals. So this distance, this distance, that distance, this distance, those are the residuals. Okay? So what are the assumptions? So like all statistical tests, there's going to be certain assumptions that have to be met before you can feel confident in your results. So if the assumptions aren't met, you could come up with an answer. So we did that with the correlations, and we tried it without meeting the assumptions, and we got really inaccurate results. So the same thing could happen here. So here's the 4 assumptions we're going to be focusing on when we talk about linear regression. Normality, absence of outliers, homogeneity of variance, and normally distributed residuals. So these are exactly the same as when we talked about correlation. Exactly, and we'll check them in the exact same way. So we'll go through those one by one. I'll mention too, this bottom one is something that's going to be unique. We haven't done this before, unique to the regression environment. We want to make sure that the residuals are normal. So we know the term residual is these distances, and we'll say more about that. Okay, let's go ahead and go forward. So normality. Well, to check for normality, we're just going to create a histogram of each of the variables. So in a simple linear regression, there is one predictor, in this case engine size. Later we'll look at a technique where you can use more than one predictor, and then you have to do this for all the variables. But right now there's just 2. So we graph the engine size, and I superimpose the normal curve, and you can say, well, it's about right. We have one car with a huge engine, so I'm not sure I'd quite call it an outlier because it sort of matches this curve. You can see there's a little bit of a skew, a little bit of a positive skew here, but it's approximately normal. We're not looking, we don't want like a bivariate or bimodal. We have a big point, or some value that's maybe way out here. So looks pretty good. Over here, horsepower, same kind of thing. It looks fairly normally distributed. In fact, it sort of matches this if you look at the little bit of the skew here. So these are very related. You can already tell from the histograms. So that's normality. So we'd graph that, and we'd basically say, yeah, they're approximately normal. Okay. Next assumption is absence of outliers. So in this case, you can see that there appear to be outliers. So here's the distribution. So this is the median, and here's our quartiles, and the lowest value and the highest value, not counting the outlier. So it does appear to be an outlier here, observation 150. Over here there also appears to be an outlier, same observation, and then 149, the next observation over, appears to be kind of out of the norm too. So we would just get rid of these for this analysis. So I put the little X over those to represent that we ditched the outliers. And then homogeneity of variance, our next assumption. So we talked about this with correlation, and the idea is we want to feel pretty comfortable that the amount of variation in our outcome variable is going to be roughly the same no matter what the level of our independent variable is. So I drew these parallel lines, so the regression line would be right in the middle of those to kind of give you a feel what I'm talking about. So if we have, let's say we have a car with a 5-liter engine size, we have about this much, or maybe go to 4.5. We have about this much variation. And if we have a car with 2 liters, we have again about this much variation. Now we notice that as we get way down here, there's not much variation, but there's also not that many values, right? Because the mean's over here. So we kind of get spread out. There's not as many values, so we're not expecting to see as dense of variation here, of distribution of variation. So we're going to say it's roughly supported. And you might think, well, what would it look like if it weren't supported? Because you keep saying that it's fine. So I'll give a comparison. This is from somebody else's website. I just took it. So this is homogeneous right here. Okay, so it's about the same all the way along. They just turned it on its side, predicted versus standardized. They just turned it on its side, but it's the same idea whether you have it diagonal or on its side. And this is an example of when it's not homogeneous. So this is heterogeneous residuals. So at one end we have everything tightly packed together. At the other end it is really spread out. So we call this fanning. So we can see that, and basically it matters because it affects our predictive power. On this end we have a lot of predictive power. Over here we have very little. So it gives us less confidence in our model. Okay, let's go ahead and pause here, and I'll pick up with the next video.